Hello, everybody, and welcome to first of our Climate Central continuing education webinars for 2018. My name is Sean Sublitz. I'm a meteorologist here at Climate Central, and joining me is Bernadette Woods-Plackey, the director of our Climate Matters program, again here at Climate Central. This is our very pretty introductory slide. I have no idea why those strange green lines appeared over at the right. But that's just the way it goes, so we'll just roll with it. Now, for those of you who are new, our Climate Matters program helps give broadcast meteorologists the tools they need to take the weather and climate change connection to their audiences, both on the air and through social media. Those of you who are already doing that, we thank you. And our webinar series is part of that program. We know not everybody can get to conferences and symposiums. Also, for those who have to leave early, or if you know colleagues couldn't make it, we're recording this and we will archive it at our website a little bit later, and you'll see it at that very long link, basically climatecentral.org, workshops and webinars. Briefly, with the flooding still going on in the Ohio and Mississippi River valleys, our Climate Matters tomorrow will be focused on trends in heavy precipitation. Of course, heavy precipitation events are getting heavier, both at the regional level and nationwide. Be on the lookout for that in your mailbox tomorrow. And now the green line has gone away, right? Bern, did you do that? I think you did it.
It's magic.
Okay, today we are very happy to have Deke Arndt, the Chief of Monitoring Branch of NOAA's National Centers for Environmental Information. For those of you who wondered or asked, how does NOAA come up with these calculations for the global and national temperature every month? He's here to give us the answers and pull back the proverbial curtain on how that is done. So if you have any questions during the course of the webinar, use your mouse to hover down toward the bottom of the screen to find the chat function and just type your questions in there and we'll get to them at the end of the presentation. With that, Deke, can you hear me, sir?
Yeah, can you hear me, Sean?
I hear you just wonderfully. So go ahead and Alt-S. You can take control of the presentation and let's roll with it.
Okay, it says I can't share while the other participant is sharing.
Well, that's just terrible.
Can you unshare?
Yes.
All right. Good deal. How's that?
That's beautiful. Now we're on it. We're on it. Go ahead. Thank you, sir.
Well, I will just.
I've got your screen just fine.
Okay. When I present, it's going to the other monitor, and I'm trying to get that fixed. But that's okay. We'll just do this.
That's fine. Whatever works for you.
Okay. So, hi everybody. I want to say hello, and I know I can get this to work. Shoot. Sorry, Sean. I got to make this work. Okay. I'm going to stop sharing that. I'm going to share again. I'm going to share my second desktop. And is that better?
That's a little bit better. Sure is.
Okay, great. All right. Thanks, everybody. Thanks for your patience while I learned some technology. I'm Deke Arndt. I'm from NOAA, the National Centers for Environmental Information in Asheville, North Carolina. And this is the commercial here. So basically, like a lot of good people who come to live an active retirement in Asheville, a lot of weather and climate data comes to retire in Asheville as well. And it ends up in our facility where we basically store it all. So it's one of the 3 world data centers for weather and climate around the world. Essentially all of the US government and some other weather and climate information end up here. And my group happens to be the climate monitoring group. I'm in the climate monitoring group. We do a little work with drought.gov, and then we also do a lot of these climate monitoring reports that you hear or see from time to time. And we utilize that deep history of climate information to try to put the recent climate into perspective. So, you know, how How unusual was it? How different from normal was it? Is it part of a trend that we're seeing or anticipating? That's kind of our job here. All right, so just a few caveats before we go. Just as background, I'm a meteorologist by training. My degrees are in meteorology. I've been in either applied climatology or service climatology for about 20 years now. I am not the lead expert for any of the material that I'm going to share. We use this science operationally, so we kind of have to know what's going on. I work with some of the world's foremost experts on some of this stuff. You know, basically how does the climate data turn itself into a credible analysis? And I also want to acknowledge there's lots of groups out there that are doing similar things with getting the most out of an imperfect climate record. So I'm going to slip up and say we, and it may sound like I'm speaking for the entire community. I'm usually specifically speaking about NOAA and NCEI's methods and practices. But I want to acknowledge that there are other bodies, both in academic and government and even in the private sector, that are doing similar work, kind of challenging how we can get the most out of the climate record. And and that's a picture of me being a drought guy at OU, which was that's kind of how people saw me there. So again, this is I think my third or fourth time to be able to do something with Climate Central. The long term is a neat program, and obviously you're being asked to do a lot and a lot and a lot across science. And so this is the climate piece of that. I know you probably get many climate questions, probably many loaded climate questions, and even outright hostile climate questions. So really what I want today is to help, help you be more confident in some of the data sets and some of the analyses that you may want to share. So trying to anticipate some of the challenges and some of the questions that you get and provide some background on that as well. All right, so this is probably one of our most visible products is the global surface temperature. So this is effectively the temperature of the planet that we report every year in mid-January. And like a lot of the graphs that we'll see in the next 30 minutes or so, this is from left to right, obviously the past on the left and the most recent times on the right. Each red dot on this graphic represents a year. The black line is the 20th century average for the planet. Years that, or dots that are below that line are years that were cooler than the 20th century average. Dots that are above the line are warmer than the 20th century average. And then the pink bars are just the average of the 10 years of a decade. And they kind of show the longer term kind of smoother filtered trend as well. So this is a pretty familiar graphic. You'll see some variant of this from whatever group is doing a global temperature analysis. And they may be slightly different where the red dots fall exactly on their version of the graph. We're all kind of singing the same song, but hitting different notes along the way. And Sean sent me some questions in advance, and one of them is like, can you explain some of the differences between the NOAA analysis and these others that we see? And I'll be glad to, towards the end of this presentation, we'll actually explain the major factors in some of those differences. All right, we also do US temperature. There's the content on this slide isn't that important other than to point out, I'm going to be focusing mainly on the global temperature from here on. The US temperature is handled in similar ways. The one difference between our version of the US temperatures and the global temperatures is the US temperatures that we use are not built using the anomaly method. And that, if you haven't heard of that before, we're about to spend 10 minutes on what do we mean by handling temperature anomalies and so on. But again, these are the types of reports that go out every month. This is, I throw this in every time I get a chance to share with people. This graphic is based on the US data. These are states that in the left two columns had their wettest or driest or coolest or warmest month on record for that month since I started working here in 2010. And then the right two columns are the same thing, except instead of months, there are different seasons. So right here, Oregon and Washington, summer 2015 towards the top of the rightmost column. That means that Oregon and Washington had their warmest summer on record at that time. So we get a lot of this. My group that I'm in, we kind of bombard a lot of information like this. This stuff kind of rolls out every month. You get a lot of this. I'm sure you get a lot of questions in the wake of this kind of information, like what's really going on out there. There's a lot of noise. There's a lot of information and disinformation and misinformation out there about climate data and how it's handled. So that's kind of the context, hopefully, of today, and what again is part of a continuing conversation between your community and ours. All right, so what are we gonna look at today? How do we compute the U.S. and global temperatures? There's probably more of an emphasis on the global temperatures because it's less straightforward. Some issues about station siting, a lot of issues about the corrections we make to the data, why we do it, how we kind of check our work. There were questions that Sean sent me that said, what's the difference between in situ and satellite-derived temperatures? Just a few kind of tools of the trade dealing with precision and dropout, and then a lot of, where can you go to find some of this stuff? So that's kind of the contents of what we'll do today. We're about to dive into some pretty esoteric stuff. If climate weren't such a kind of a touchy topic out in the real world, a lot of this stuff would be handled by a small group of nerds that would be perfectly happy doing this. But because it has taken on a deeper meaning in the national conversation, the good news is that has led to a very intense scrutiny of the climate record and the temperature record. And that has really improved our work. It's really improved our transparency. It's improved kind of the confidence that we have in our own work, knowing that this kind of scrutiny is ongoing. So it's really led to a better product. And that, again, not just for NOAA, but for all of these groups that are doing this work, really kind of groundbreaking stuff. We're going to focus on temperature, but I just want to use this slide to back out to the really high level view. A lot of people, when they get animated about climate and climate change and the temperature record, often forget the context that the temperature record sits in, and that it is one indicator among dozens of indicators that all point towards a warming world. Because temperature is really familiar, because most lay persons are pretty familiar with the way that we observe temperature, and just because there's a lot of information out there, people tend to gravitate towards temperature as this single indicator of climate change. But in fact, all of these elements on the board, all these variables on the board in concert are pointing towards a warming world. So before we dive into the how-to, just a couple definitions. I'm going to use the word anomalies. Our communications pros usually remind us to not use the word anomalies because that sounds like something that makes a spaceship fail. But what anomalies are, they're just departures from a baseline, typically some kind of normal, whether it's a 1981 to 2010 normal or whether it's a 20th century average. An anomaly in the language that I'm using today is really just a departure from some agreed upon baseline period. So a positive anomaly, I'll probably say that. That just means the observed temperature was warmer than the baseline, and a negative anomaly means an observed temperature was cooler than the baseline, if that baseline was a normal or a 20th century average or so on. And then this figure on the right, I just pulled that from North Dakota, Bismarck, North Dakota, and it shows, it's basically the Weather Service daily observations for Bismarck this month. And column number 5, DEP, is departure. So that just is a column that's showing how different that day's temperature was from the normal. and that is exactly what we would call an anomaly in our climate work. So that's kind of the Weather Service equivalent of that. Just like when you communicate that today was the average temperature or the high temperature was 12 degrees above or below normal, just in this little community, we call that an anomaly. So why do we use them? And now we're diving into global temperature. So we work with temperature anomalies more than we work with the raw data. We start with the raw absolute temperature observation, and we immediately compute these anomalies, these departures from normal, and then we work with those because the math is a lot cleaner, and it takes advantage of some meteorological properties. So here's an example on the right of 5 stations near me here in Asheville, and this is the average annual temperature for these 5 stations for 7 or 8 years early in the century. And there are 4 stations that are low elevation stations and a 5th that's on top of Mount Mitchell, which is the highest point in the eastern United States. And so its climatologically, it's a lot cooler side. It's 10 degrees cooler on top of Mount Mitchell on a given day than it is here. So if there were issues with the Mount Mitchell station and it all of a sudden disappeared, if we were averaging these 5 values together and we dropped out Mount Mitchell, we would kind of artificially warm up the area really quick. But the fact is, the anomalies, each one of those years, the difference from average is pretty consistent thanks to meteorological timescales. It's generally speaking, if it's a warm day here in downtown Asheville, it's also a warmer than normal day on the top of Mount Mitchell, even though our absolute temperatures would likely be about 10 degrees different. And this becomes truer and truer as you increase the time scale. So while you can imagine some scenarios where it would be a cooler than normal day here and a warmer than normal day on top of Mount Mitchell in a given day, over the course of a month, it's almost a guarantee that if it's a warmer than normal month here, it is going to be a similarly warmer than normal month at nearby meteorological stations. So that's the advantage of anomalies, is we can really deal with both station dropouts and be truer to meteorological scales as well. So that's why we typically work in the anomaly space. We take the raw value, we subtract some normal from it, we're left with this anomaly, which then we combine with many other anomalies to come up with these fields. The purpose of this slide was just a gee whiz slide. These are 3 different annual temperature anomalies since 1900. So the green one in the middle is the global temperature anomaly. It's the same data that we looked at earlier with the little red circles. The dark blue line is the continental contiguous United States, the lower 48, the anomaly, how different it was from its own 20th century average. And then the dotted line is Oklahoma. And the whole point of this slide is to show that as you go larger in scale, anomalies tend to dampen out. There's less noise. As you go smaller in scale, a given year, especially a month, you can see very large swings from the baseline. So this is just to show you that a 2-degree anomaly on a global scale would be huge for a year. A 2-degree anomaly for Oklahoma in a given year would be largely in keeping with the typical noise around the baseline. So how do we compute the global temperature? We do it a little differently between, and I say we, I'm talking about NOAA now. The other groups have their own methods. They're largely similar, but the details are different. For us, for land data, we derive the global temperature from grid boxes. So we compute 5-degree by 5-degree grid boxes. So I've basically highlighted a single box in Australia, and then we're going to go through a hypothetical example of where the anomaly, where the departure from average is coming from within that box, according to our methods again. So we, in this case, these are stations. So I have stations A through H in the gray box. So that's recasting that box in Australia, and that may be the layout, the map of the meteorological stations that are available that have both an observation this month and a normal that we can compare it to. So let's say we get lucky and there are 8 stations that are eligible in that box. So we start with those 8 stations. We compute an individual station anomaly at each of those. So we've started here. Again, this is a scenario where we have the normal temperature represented on a scale, so to speak, from station A through station H. G is climatologically the warmest station of the bunch. A and D are climatologically the coolest stations of the bunch. And then we take this month's or this year's or this day's temperature in green. So the green are the observed, the blue are the normals or the baseline, and then we compute an anomaly. And in this case, all 8 stations are warmer than the baseline by some amount. And that amount is represented by the length of this red arrow. So we take those 8 anomaly values, we scrap the original OBS, and from now on, we're just working with anomalies. And here are those same 8 arrows kind of lined up next to each other. They're all positive, meaning all 8 stations had a warmer than normal month. That's pretty typical. And then we get an average anomaly. So that big red arrow is the average of the 8 anomalies from Australian stations within that Australian box. And we come up with a grid box for that 5 degree by 5 degree value. And then we basically average all of the grid boxes on the planet together, recognizing that the grid boxes nearest the equator, 5 degrees longitude, is a lot bigger than 5 degrees longitude at a high latitude. So we have to correct for that. And we essentially come up with the global temperature anomaly. And it's the methods for the ocean boxes are slightly different, but not a whole lot different. It is about comparing a large number of current observation with a huge number of historical observations and coming up with box by box values. All right, so I think most of the questions were less about like how do you do it and more about like what are the things that can go wrong and how can we respond to some criticisms of the way we do things. So one thing that a lot of people have to deal with are the difference between, there are 2 threats to validity in the data, generally speaking. One are kind of the random errors within the data. So flaky stations, things that kind of happen from day to day or month to month that mess up with data. And then there are bias. So we're going to go through some details of each and some analogies of each. But the garden variety bad data and random error doesn't really worry us. We're okay over, the power of large numbers. Statistics helps us here. If they are truly random errors that kind of bounce around the average over large scales, they end up kind of canceling each other out. And we'll go over some details in this. What keeps us up at night and what keeps people that are doing this kind of work in the business and continuing to push ahead to improve things are systematic biases, things that shift multiple stations in the same direction at approximately the same time. So things that can move an individual station's record up or down kind of semi-permanently. And we call those biases. And we'll go over some examples of these. But you can think of some of them, the encroaching of an urban area on a formerly rural station, or the movement of a station from one elevation to the next. At the station level, those can be biases that are introduced to the record that kind of need to be detected and corrected. Changing instrumentation, changing the time of observation. Those are all things that we're about to jump into. So some examples of random error, and this is a little bit of a different fit, but a lot of times we get asked, we give temperature of the planet down to hundredths of degrees Celsius when the daily data may be only or rounded to the nearest degree Celsius. And how can we do that? And again, the answer goes back to that power of large numbers. When you're rounding is one of those random things that kind of pushes things equally up or down, especially if you're using modern rounding techniques. They're very random. So the power of large numbers really helps those things equal out. And then a good follow-up question, a very understandable follow-up question is, well, what about, the instrument's only reliable between plus or minus, so many values. Again, these are the types of non-biased random issues that thankfully on a large scale tend to kind of forgive themselves. And, one way to think of it, I like basketball and football analogies, is, we say that LeBron James, we've calculated that he's a 33.2% three-point shooter. And how can we say that when, he's basically three-point shots are just ones and zeros, right? So because there's so many samples in LeBron James' three-point shooting history, we're able to take this really binary input, he either made it or he missed it, and come up with a really more sophisticated and precise way of telling a story. So, and that's a similar way. In a very similar way, we're able to overcome some of these issues just because there's a lot of data. So again, random error forgives itself when the scale is large and the number of observations are large. And so in the basketball world, again, the random error would be, they called it a two-pointer when it should have been a three-pointer, or he got fouled, so they shouldn't have made it. And those are kind of random things that can happen with each individual shot. And again, over the long term, those forgive themselves. Those kind of occur at random rates. However, and this happened to Michael Jordan, the three-point line could move during their career. That's a bias. So if the three-point line moves a foot and a half back, almost every shooter's three-point percentage is going to go down. And that's something that someone looking at, three-point shooting from a climate perspective would need to account for in their analysis. Points to make here, again, to repeat, that's the bias, not the random error, that really keeps data people up at night, keeps us working on stuff. The causes of bias are often changes in the instruments themselves, or changes in the way and the timing and the practices that we use to employ those instruments. And a lot of times the hints to solving these bias issues lie in the metadata. I won't go much more into the metadata, but it's an important piece of collecting information that the people that are working on these problems really explore. All right, so what are the drivers of these biases? Time of observation changes, we'll go into the detail on that. Changes in the instruments themselves, we'll go into some detail on that. Changes in the surroundings of a station, we'll go into detail on that. All of these can be documented or undocumented in the metadata associated with the station. So our algorithms need to be able to use what we know in the documentation and trust in the documentation and help determine if we're finding the undocumented samples at a satisfactory rate. This image on the right is Reno, Nevada, which if you followed this kind of work over the last, it's kind of the poster child for these types of shifts. The ASOS station at Reno got yanked up and down the runway several times in the 90s and introduced some really obvious biases to the observing environment. So there's a lot of work done using this Reno record. Okay, so time of observation. We are now, for our cooperative long-term volunteer once-a-day observing stations that are taking daily values, we are now a nation predominantly of morning observers. We used to be a nation of evening observers. And what this means is, depending if you have a sharp frontal passage in particular, you can double dip in the morning. You can count the same morning's cold temperature as the low for the day before, and then it can preserve itself as the low for the day after. Whereas on an afternoon temperature, if you're taking the temperature every afternoon, you have a really hot afternoon, especially with a subsequent frontal passage, the high temperature that you observe in the afternoon on a given day could influence, or could be the high temperature for the day before, and then it could also end up being the high temperature of the much cooler day that follows. So it's kind of a double sampling effect. The fact that we were evening observers and became morning observers in a vacuum, and nothing is in a vacuum, but in a vacuum, that introduced a cool bias over time. And so the time of observation correction is basically a statistical correction for that effect. And it's probably one of the least controversial of the or at least the least talked about of the changes that we make, but it's actually one of the largest corrections to the record as a whole, because these were systemic. These were, if people randomly changed back and forth from being evening morning observers, it wouldn't be as big a deal. But the fact that there was a general migration towards morning observing, that's actually something we need to account for. On all of these slides, I'm trying to link to the one of the journal articles that really describes the phenomenon. So if you really are interested, you can read for yourself. Okay, so another thing that's also pretty obvious to a lot of people and gets kind of reshared and is part of the noise surrounding climate data are changes in instrumentation and changes in the station environment. So one of the larger changes in the US record, and the US is a little unique compared to the rest of the world, is a lot of the cooperative observers, which are, again, are the backbone of our long-term historical record, moved from liquid and glass thermometers and these wooden shelters, like in the middle of my screen here, to these MMTS, these electronic thermistor sensors in these more honeycomb shelters. And these kind of had competing effects. The shelter itself, generally by and large, went from a warmer afternoon shelter to basically a better ventilated shelter, so that had a cooling effect. At the same time, the electronic instruments needed to be powered and tethered to some kind of data logger recording equipment, so that generally brought them closer to civilization, closer to buildings, closer to structures. So these had kind of competing effects. So the corrections, and we're about to get to the big US temperature total effects slide. Then there's also urbanization, which is a kind of a well-known phenomenon in that as urban areas creep closer to or more completely around an observing site, that this can generally increase temperatures, particularly morning time or minimum temperatures. And there's also a similar phenomenon in the middle of the 20th century where a lot of downtown stations became rural airport stations. So there was a less discussed ruralization phenomenon in the kind of early to middle 20th century as well, kind of around the run up to World War II. So this is a quote, I believe, a direct quote from a paper by a fellow named Zeke Hausfather. He's one of these other groups. He's in one of these other groups that's really doing good work and kind of helping check our work and advance the knowledge of the community. But our homogenization, basically detecting these breaks in the station record, effectively captured and removed the encroaching urban signals. So one of the things you'll hear about the NOAA US temperatures, we don't explicitly account for urban heat islands, and we don't. But the algorithm that we use to detect changes in a station's record effectively, even though it's not explicitly looking for that, kind of finds and captures and kills most of that signal. So total effect on the contiguous US temperature, before we do any sort of homogenization, so if we would let the US data kind of in the raw form speak for itself, a lot of the changes that happened both in the time of observation and in the shelter environment of the cooperative stations basically artificially cooled the afternoon temperatures and, generally speaking, warmed the minimum temperatures. So they kind of work in opposition, but the corrections that we employ attempt to correct for these. So how do we know the things that we're doing? So effectively, we have algorithms that try to go identify breakpoints in a station's history, decide whether we have enough competence to create a segment on either side of that, a before and an after period, and then make a correction where we reconcile that before and after period. And how do we know we're doing this well? So one is we stress test the algorithms, basically in a methods that were blind both to the authors and to the algorithms themselves, basically through a bunch of different scenarios where we artificially changed lots of data and kind of fed this artificial data set into the algorithms to see if the algorithms could detect them. And by and large, these were different scenarios. This was like major instrument change or gradual urbanization or, you know, any of the scenarios that you can kind of think of. And generally, the benchmarking experiments, they basically said, yes, the algorithms tend to correct things back in the right direction, even if they don't completely make the correction. So the corrections tend to correct in the right direction in the vast majority of the cases. And then finally, comparison to the Climate Reference Network, which is deployed early in the 21st century to do exactly this, to serve as a reference for the many weather networks that were out there. And we see pretty darn close tracking between our current CONUS temperature and the Climate Reference Network. And then this is the same graphic, just looking back towards the entire record. And so you can see very high performance on the Climate Reference Network, which are a bunch of pristine rural, you know, locations, often in remote areas of national parks that won't have a lot of these issues that challenge their validity. All right, so some questions that we get: why do we adjust when we make these adjustments? Why do we adjust the past and not the present? And the rationale behind that is that the data sets should reflect what the history would show if we were using today's fleet of observations and practices. That's why when we need to make a correction, when we see that a station has a break point and we need to reconcile them, we will bring the past in line with what we're currently observing. We save, contrary to what you may hear out there, we save the unadjusted data, and these are always publicly available. We do not change the data. And we use this unadjusted data each month. So each month we make a series of assessments and corrections at the station level, thousands of stations, and then we go right back to the raw data the next month. So we don't just assume that a correction from last month is still valid. And a lot of these are because these algorithms are really conservative. And then on the right, this is my one self-serving slide. If you take anything away, this is a graphic that shows what the global temperature would look like without our corrections in green and with our corrections in dark gray. And our corrections, globally speaking, are reducing the warming rate seen in the raw data. So you may hear that we are pushing the needle on the global temperature, and we're just pushing it in the opposite direction than what many people believe and claim. We actually reduce the rate of warming that we see in the raw data with the corrections that we make. And that has a lot to do with sea surface temperatures. So oceans take up 2/3 of the globe, and the way we've observed ocean and ocean marine air temperatures have really changed, especially relative to changes in the land observations. So these three pictures represent three general dominant eras over the last 150 years or so. On the left, we used to take ocean temperatures by throwing a bucket over the side of a boat, and that had its own quirks. And that kind of was the dominant method up through the first half of the 20th century, with an abrupt interruption during World War II, because people didn't want to be standing out on the deck in hostile situations and kind of scary travel. So the engine room intake during World War II became the dominant method, and that basically is measuring water temperature as it makes its way through a ship's plumbing toward the engine room where it was used as a coolant. That was used widely during World War II, and then generally in the years that followed World War II became the dominant way of measuring ocean temperatures. And then kind of in the 90s and on, buoys have become or are becoming the dominant kind of platform of observing temperatures. And so each of these has its own issues. I'm happy to talk about them in Q&A, but in the interest of time, correcting for the general shifts in these three eras of ocean temperature assessment are what largely drives that change in global temperature. And that going back to this slide, this mid-century adjustment where you see before the 40s, generally we make a fairly significant adjustment to bring the prior years a little warmer, thereby reducing the rate. That had a lot to do with the change from that bucket method to the engine room intake method. This is just a graphic that shows the distribution of temperatures. So in the dark gray, these are the proportion of ship observation or SST observations that were taken with buckets. And then this lighter gray are those that were engine room intake. And then the hatched area here are the proportion of buoy measurements among the global fleet. And then this remaining light gray is kind of the yet to be determined using the metadata version. So you can kind of see that buckets have fallen out of favor. Engine room intake had its heyday in the mid to late 20th century, and now buoys are the dominant observing platform around the world. A few other random things. We had a question about satellite versus surface temperature. And so on the left, we hear these conflated a lot, especially during impassioned arguments about climate. Surface, what are the differences was the specific question that we had. So surface temperature is trying to estimate what you and I would call surface temperature, which is a few feet, 5, 6, 7 feet above the ground using a meteorological apparatus. It's measured by exactly what you think, thousands of in situ stations. And our data sets and some others, GHCN, the US Climate Division data set, the Crew Temp, which is a British outfit. Those are the main, or some of the main data sets that you might see. What are the challenges to those? All of the ones we covered. The drifting, the changes in the station environment, and the changing in the instruments and the practices themselves. On the right are the satellite observations. And technically the one that's typically used to compare to the surface temperature is the lower tropospheric temperature. And so what that literally is a slab. It's the average of a slab from the surface to about 26,000 feet. It's weighted, so the middle part of that layer is measured a little more proportionally than the upper and lower parts of that layer. It's measured by, it's an indirect measurement, so there's basically radiances and microwave frequencies that are picked up by the satellite. That's run through kind of an atmospheric model and some assumptions about emissivity, and the slab, the layer temperature is kind of backed out of those observations. Some familiar data sets are RSS, which is a private company that does this kind of work, and University of Alabama Huntsville, which kind of pioneered the method. And the challenges that are satellite challenges are orbital drift. So the satellites that are measuring these things aren't passing over the same place every day at the exact same time. Over time, there are orbital drift corrections that need to be made. When an instrument changes, when you replace satellite X with satellite Y, that is a massive change that needs to be reconciled. So there's a lot of challenging work in doing that. So essentially, they're not the same thing. The surface temperature is the surface temperature. The satellite temperature is really an average temperature of the lower troposphere. And they each have unique challenges, and they're measured different ways. We already talked about precision, so I'm going to skip that and just finish with 4 specific questions that Sean sent. Someone asked, I'm curious about the early years, when we didn't have a lot of data, how did we get global averages for those years? And the oceans and even Africa are a little better sampled than you might think, but there was enough coverage around the world to make a credible monthly temperature anomaly estimate. We stop at we start our record at our official record at 1880. Some groups extend those back into the mid 1800s with varying levels of confidence. With all of that said, the uncertainties really before the turn of the 19th to 20th century generally are higher, particularly because of the sparser coverage. But there is not complete global coverage, but there's kind of quasi-global coverage. And in any given month, a large region, it is conceivable that a blob of really warm or really cool air mass could have hung out over a region during an individual month and not been sampled well. But again, the power of many months stacking up, you're not going to hide the same colder than normal air masses for hundreds of consecutive months. So the long-term signal is actually fairly robust. How are future analysis looking? Do we lean more on surface station or satellite obs? Satellites are going to continue to become more important over time. They're really dense with their data. They have their own unique quirks and issues. I think they're going to be especially important for basically everything but surface temperature and maybe precipitation, although satellites add a lot of coverage for precipitation that we don't see. So I think they'll continue to be important. They'll become more robust the longer the record can make. The advantage that the in situ network has over the satellites now is that they were started about 100 years earlier, 150 years earlier, and we can use the heterogeneity within the network to really evaluate one station against each other. Without getting in the weeds, what are the key differences between NOAA and some of the other groups? So abbreviated version, the main difference is how aggressive we are in kind of extrapolating or interpolating over data sparse areas. So the Arctic is an area so we're fairly conservative. We're probably on the conservative side of the 50-yard line compared to some other groups. NASA's somewhat aggressive in interpolating over data sparse regions. The areas that we tend to sometimes not analyze are the Antarctic, the high Arctic, and parts of Central Africa. Of those, the Arctic is warming at a substantially higher rate than the rest of the planet. So groups that are interpolating over the Arctic, as long as the entire Arctic is in a given year or month fairly uniformly, there isn't a lot of significant detail within that. So like this NASA map where you can really see where they filled in some really warm temperatures up near the pole. As long as the pan-Arctic situation is relatively homogeneous and is able to be captured by the high latitude stations that they have, they are going to capture that. And for most of this decade and the decade before it, the Arctic has been quite a bit warmer. So, just full disclosure, we're working in our group to kind of come up with a way to interpolate across the Arctic because we need to capture that signal kind of with our typical conservatism in approaching those things. Africa and the Antarctic, as far as we can tell, those represent, again, fractions of the Earth's surface, but they don't have this systematic change relative to the rest of the planet. It's really the Arctic that is driving some of the differences in recent years. We also do some different things with how we handle stations, kind of throwing in unique stations that are part of each one of these groups, kind of individual holdings, how we handle missing data, some quality assurance, quality control methods. We also report against different base periods, which can be annoying, although it doesn't have an effect on trend analyses. But sometimes it makes it difficult to compare map versus map. Like these two maps, that's our map on the top, that's NASA's on the bottom. We're comparing to the 81 to 2010 period, which is slightly warmer climatologically than the NASA period of 51 through 80. So our map's a little bluer than the NASA map because we're comparing today's temperatures to a slightly warmer period. And then the last question is there a way to know how much data is discarded or deemed inferior for analyses? So there's two ways to look at these. One is the garden variety bad data, and then the other is this bias correction. So the flag rate for individual or monthly observations are about 0.25%. So basically 1 out of every 400 observations is rejected by our quality control techniques just for reasons that that occur. You know, there's too many missing days in a station, or there's, you know, it's clearly out to lunch, it's reporting 150-degree temperatures or something like that. Or there's logical inconsistencies, like one day's minimum is warmer than the maximum, stuff like that. So the flag rate is about 0.25% for those. In the bias correction, the vast majority of stations globally have at least one break identified in the record, and most stations have a couple. And so if that is what you're getting at, there are very few stations that have been observed around the world exactly the same way, with exactly the same instruments, at exactly the same time of day, at exactly the same spot, by exactly the same organization. The reality is the vast majority of stations do have something that happened in their history that would have introduced some sort of shift in their record, and we detect and correct for those. When we find those, our algorithms happen to be pretty conservative, and it takes a lot of evidence to convince our algorithm that there was a break in the record. And if there is a break in the record identified, if the most recent segment is long enough to kind of qualify as a new segment, so if it's more than a few years, if it's a decade or so, we'll call that a segment. If the bias detection is very recent, we will basically not use that. We'll shelve that data, and we'll basically wait for more evidence to pile up so that we can identify a longer segment in the future. I hope that helped. That was kind of an odd answer, but I didn't know what the initial question was getting at. So those are two answers to the same question from kind of two different perspectives. And then finally, I'll stop here. I'll share this with Sean so people can go through, and these are just different resources that you may want to use or may not want to use if your viewers or if you are interested in diving in more. And I'll stop there and hand control back over to Sean.
Well, before you do that, Deke, thanks. I want you to hold control, because Zeke actually had a question that he chimed in, and want to give you an opportunity to address that. He said, for the land grid boxes, are you weighting both by latitude and land area? For example, grid boxes with large lakes and oceans.
Yes, thanks. So yes, latitude, and then when we combine the land data with the ocean, the SST data set, yes, it is weighted by land versus ocean weight. I don't know if large lakes, the Great Lakes, I don't think are part of that. But as far as ocean versus land, yes. If a grid box is 30% land and 70% ocean, we'll use 30% land data, 70% SST for that box.
Good deal. Vern, did you have some things? You looked kind of curious over there.
I did have some things. First of all, Deke, I mean, we cannot thank you enough. You always do such an amazing job with this. And so everyone knows Deke has been really a data superhero to us through the whole time I've been here. You know, he's so responsive and helps guide us through some of our projects when we have questions about data. One thing that's come up in the past couple of years, though, that I never had a chance to really have a conversation with you about is, I understand why we track normals the way we do now. The baseline you use, the baseline that NASA uses. But since the global conversation has shifted now to this cumulative warming goal of 2 degrees Celsius from pre-industrial times, one thing we've done is when your global numbers come out, we use yours and NASA's, and we re-baseline them back to 1880 to 1910, since that's the earliest reliable baseline that's available. And I was curious if there's been internal conversation. I've seen you guys release it with respect to that early industrial baseline sometimes, but not necessarily consistently. So I was curious how you guys felt about that.
Yeah, so we have had a lot of internal conversations about it. And if we get, basically, if Congress kind of tells us to produce that, what we'll do is exactly what you did. We use 1880 through 1900. I don't think through 1910 would be substantially different as a surrogate for that pre-industrial average. We are in a low grade kind of way, having conversations like how do we do this consistently? How do we document it? How do we make this public? And there's a lot of homework that we have to do on our end before we can just throw something out there. I mean, it's one thing to respond to a query from a constituent or an office holder and explain your methodology kind of on the fly, but it's another thing to kind of routinely release information. So we have a lot of homework in front of us to find the best way to do that. But for now, if we do have a quick turnaround request, we basically take those 21 years and claim them as a surrogate for a pre-industrial average, which is probably pretty darn close to the truth.
Thank you. That is interesting. I mean, I'm sure, yeah, when you guys have to take it on, it has to be in a very documented, extensive way. It's just always, it's interesting how I've tried to explain to people too, that the reason you've done it is because that's for priority audiences. It's only recently that there's been this global conversation shift, and that's why we've been able to do it.
Yeah, if that global conversation shift would have happened 10 years ago, we'd probably be doing it routinely by now. It's just, we need to catch up too. Absolutely.
Takes a little while. Understand. Thank you very much. Appreciate that.
Great. We're coming up on the bottom of the hour, so it's been a full hour. It's been a good hour. And Deke, again, as Burdette says, I want to thank you very much for spending the time with us. A lot of good information here for our meteorologists to take back to their stations, their viewers, so they can answer those questions that sometimes are nagging them. So thank you very much for spending time with us this afternoon.
Thanks, guys. Thanks for everything you do, both Climate Central and the folks on the call. Appreciate it.
All right, everybody. Thank you very much for joining us. We're going to get this thing recorded, and hopefully we'll get it uploaded to our website in the next couple of days or so. We'll see how that goes, time being what it is. And if you have any questions, don't hesitate to email Bernadette or myself. Otherwise, I hope you enjoy the rest of your afternoon. Bern, do you have anything else?
No, just look forward. Our Climate Matters tomorrow. Sean already teed it up.
Yep, heavy rain, heavy rain, heavy rain. It's all.
Oh, I do have one additional.
Yes, of course.
We're bringing back one of the crowd favorites. And so many of you loved Climate Change and Beer for St. Patrick's Day a few years ago. We will be revisiting that in 2 weeks.
Right, and for the Wednesday before St. Patrick's Day. All right, everybody. Thank you very much. Enjoy the rest of your afternoon. Have a good weekend. We'll talk soon.